All right, let's talk about Module 4 of the eCTD, the Electronic Common Technical Document. If you're building a new drug submission, this is your starting block. It's the entire non-clinical story, the bedrock of everything that comes next. So let's get into it. So here's the big question, right? It's the one that every single drug developer on the planet has to answer before they can even think about starting a clinical trial. The responsibility is just immense because we're talking about human safety. And the answer, the whole story, is packed into Module 4. I like to think of Module 4 as the complete biography of a drug before it ever meets a person. It's the whole non-clinical dossier. We're talking every experiment from the very first test tube studies all the way up to complex animal models. It's the massive pile of evidence you hand over to regulators to convince them it's okay to move forward. The easiest way to think about Module 4 is that it answers 3 core questions. And the first one is the most fundamental of all. Does this drug actually do what we say it's going to do? And that, my friends, is the world of pharmacology. So pharmacology is all about what the drug does to the body. We're looking at every level, from how it interacts with a single molecule all the way up to its effect on a whole living system. We look at the main effect, the thing we want it to do. That's called primary pharmacodynamics. But, and this is crucial, we also have to hunt for any other effects it might be having.
Okay, let's make this real. Let's pretend we've made a new painkiller called popcorn medicine. Primary pharmacodynamics is where you show the proof in the pudding. You'd have a study showing, yep, our drug physically binds to its target. This enzyme we'll call pain kinase. But that's not enough. You also have to show it has a real effect, like actually reducing pain scores in rats. That is your preclinical proof that this thing works. But what else is the drug doing? That's where we get into secondary and safety pharmacology. Secondary pharmacology is like a background check. We're looking for any other molecules it might be sticking to. And then safety pharmacology gets really serious. It's governed by strict international guidelines and looks at the drug's effect on the absolute vital systems, the central nervous system, the cardiovascular system, and the respiratory system.
And here's a perfect example of why this stuff matters so much. Let's say in a dog study, our popcorn medicine caused a drop in blood pressure, but only at doses way, way higher than what we expect to use in humans. Now, this doesn't kill the drug. Nope. Instead, it sends a crystal clear message to the clinical team. For your phase 1 trial, you have to monitor blood pressure like a hawk, start with a super low dose, and increase it very, very slowly.
Okay, this number, this is a big one. It's tied to one of the most critical safety tests there is. It's called the HERG assay, and it checks if a drug might cause a fatal heart arrhythmia. It's a huge deal. Regulators have a hard line. You need at least a 30-fold safety margin between the dose that causes this effect in a lab and the highest dose you expect in a human. Hitting this 30x margin, like our popcorn medicine did, that's a major, major milestone. All right, so we've answered question number 1, does it work? Now for question number 2, what does the body do to the drug? This is a story of the drug's journey, and we call it pharmacokinetics. You'll hear the term pharmacokinetics, or just PK, all the time. And it's almost always talked about with the acronym ADME. That stands for absorption, distribution, metabolism, and excretion. We have to study how the drug gets into the body, where it goes, how the body breaks it down, and finally, how it gets rid of it. This stuff is absolutely essential for setting our safety margins later on and for predicting how it's going to behave in people. Let's check back in with our popcorn medicine to see how this plays out. On the left, we've got absorption. The data from rats shows a 55% bioavailability when given orally. Awesome. That tells our chemists they're on the right track for making a pill. On the right, we have excretion. We see that about 2/3 of the drug leaves the body through the kidneys, and that immediately raises a good flag, that we need to pay close attention to kidney function in our human trials. One of the coolest studies in this whole section has to be the QWBA. What we do is tag the drug with a tiny, safe, radioactive label. Then we can see exactly where it goes in the body. It's literally like looking at a heat map. For our popcorn medicine, the map is great news. It's glowing hot in the spinal cord, which is our target, and just as importantly, it's cold in sensitive places like the brain and testes. It's powerful proof that the drug is going where we want it to and not where we don't. Okay. So we've shown it works, and we know how the body handles it. Now we get to the big one, the largest, the most expensive, and the most time-consuming part of Module 4. We have to answer, with as much detail as possible, what harm can it cause? Welcome to toxicology. So with toxicology, our job is basically to try and break the drug. Seriously. We intentionally give animals increasingly high doses over different lengths of time to find out what can go wrong and at what level. The whole point is to define that all-important safety margin, the gap between a dose that helps and a dose that harms. If there's one single concept you take away from this whole toxicology section, please let it be this one, the no AEL. It stands for no observed adverse effect level. It is the North Star of every tox study. It's the highest dose we tested where, basically, nothing bad happened. That no AEL becomes the bedrock for calculating a safe starting dose for humans. It's everything. So how do we find that NOAEL, especially for a drug that someone might take for years? Well, that's where repeat dose studies come in. They can go on for months and months. And here's the key. They are always done in two different species, usually a rodent, like a rat, and a non-rodent, like a dog. Why two? Because you just can't trust that one species will tell you the whole story. And this is the perfect illustration of why. With our popcorn medicine, maybe the long-term rat study pointed to the liver as the main place toxicity shows up, but then in the dog study, the liver looks totally fine, but we see a slight effect on the heart. See, one species told you to watch the liver, the other told you to watch the heart. Neither one was wrong, but you absolutely need both to get the full, reliable safety picture to guide you in the clinic. Now, there's a special area of tox called genotoxicity, basically asking, does this stuff damage your DNA? There's a standard 3-part testing battery for this. You start with the Ames test in bacteria. Then you move up to mammalian cells in a dish to look for bigger chromosome damage. And finally, you confirm it all in a living animal, usually a rat. Getting a clean bill of health across all 3 tests, well, that's a huge sigh of relief for any drug program.
Okay, so you've done all these studies, years of work, millions and millions of dollars spent. What do you actually have at the end of it all? Well, you don't just have a pile of reports, you have a story. You have a complete scientific argument that you're about to present to the world's toughest critics, the regulators.
This is your case. This is your argument boiled down. You're standing up and saying, look, it works, that's our pharmacology. The body can handle it, that's our pharmacokinetics. And it's safe. It doesn't mess with DNA, it doesn't cause birth defects, and it's not going to cause cancer. And based on all of that, the safety margins we've established are totally acceptable for us to begin testing this in people.
And just remember what it takes to build this argument. The price tag, it's absolutely staggering. To generate a full Module 4 package, you are very likely looking at something in the range of 20 to 50 million pounds. It's a massive investment.
And it's not just about the money. It's about time. A lot of time. From start to finish, completing all the necessary studies for Module 4 typically takes somewhere between 3 and 5 years. All of this has to happen long before that first human volunteer ever takes a dose. And that really brings us to the core of it all. Module 4 isn't just a box-ticking exercise for the regulators. It is the absolute foundation that your entire clinical program, your entire company, maybe, is built on. Any weakness here, any crack in that foundation can bring the whole thing tumbling down later. So when you're putting it together, the question you have to keep asking is this foundation solid enough to hold the weight of everything we're about to build on top of it?